I'm Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth.
Hello everyone and welcome back. Today we are continuing our discussion of AP Physics 1 Unit 1, which is kinematics. And today we are continuing with our talk about the second half of that unit, which is two-dimensional motion. In our last video, my fellow Beth talked to you guys about how to take a vector and break it down into its component pieces. So if you're traveling northeast at a certain speed, how fast are you moving north and how fast are you moving east? Well, today we're going to now do that in the opposite direction. If we have our component pieces of a vector, how do we combine them back into a single vector? Let's get started, shall we? So let's say we have the component pieces of our vector. So we have our x component and our y component. And let's say that our y component in this instance is like maybe 2.5. And of course, in physics, all numbers are meaningless without units. So let's say that this is meters per second. Let's say this is a speed. Then let's say in our x direction, we have 4.33 meters per second. I will never pass up an opportunity to talk about my cat. She's adorable. So let's say that in this example, my cat Juniper is running east at 4.33 meters per second and running north at 2.5 meters per second. She is a very fast cat. So then what is our total vector here? What do we get when we combine them? Well, we have just a little triangle here. So whenever we're talking about vectors, there are two components we need to think about, right? Vectors all have direction and momentum, or r and theta. So those are the things that we're looking for here. We're looking for an r, or a magnitude of our vector, as well as theta, which is our direction. So let's first start trying to solve for the magnitude of our vector, this r here. Well, here we have a lovely triangle. We've got an x and a y, these are two sides. So if we go back deep into our memory banks, back from algebra, we might remember our old friend the Pythagorean theorem, where a squared plus b squared equals c squared, right? So if we use this and we solve for c, all we have to do is take the square root of both sides, and we end up finding that, hey, c, the hypotenuse of my triangle, is equal to the square root of a squared plus b squared. Well, we're just going to do that exact same math here in order to solve for the hypotenuse of this triangle here. And that's it. Vectors sound scary, but they're really just triangles a lot of the time. So let's just do that. We have the x component of our vector here is 4.33. So we have 4.33 meters per second squared plus the y component of our vector, 2.5 meters per second squared. We're going to take the square root of that, and that is going to give us our total vector here. So what is that? Well, we have 4.3 squared plus 2.5 squared, and then the square root of that. If you plug that all into your calculator, you end up finding that this is about equal to 4.97, but we know sig fig, so we're just going to change this to about 5.0 meters per second. So that is our r here. That is the magnitude of our vector, is just 5.0 meters per second. And that's really all there is to it. Don't let the fact that, we've got triangles and trigonometry and vectors with multiple components and all of these things going on. You're just using the Pythagorean theorem, and you've done that a bunch of times. You're old hats at that by this point. So now, we've solved for the magnitude of this vector, but vectors also need one other thing, which is our direction, right? And we're going to represent our direction by this angle here. So last time, in our last video, my fellow Beth talked to you guys about how you can use SOHCAHTOA in order to solve for different angles in a triangle by using a relationship between the sides and da-da-da-da-da. And she introduced a fun little acronym that I still say to myself every time I approach a trig problem, which is SOHCAHTOA. I had a student who mentioned to me the other day that she always has trouble remembering SOHCAHTOA, or remembering things in general, but she never has trouble remembering SOHCAHTOA because she's a big Star Wars fan, And SOHCAHTOA sounds a lot like Ahsoka Tano. So if you have trouble remembering SOHCAHTOA, but like Star Wars, well, now you won't have trouble remembering SOHCAHTOA. But that's what we're going to be using here. So we've got theta, we have two sides, and we're trying to solve for this unknown angle theta, and we're just going to use SOHCAHTOA for that. So here we have our x side. Well, this side is our adjacent side to angle theta, so we know we're going to be looking for something with the with an A in our little angle relationship. And we also have our y side here. This is opposite of our angle theta, right? So if we look at SOHCAHTOA, and we're trying to figure out if we want to use sine, cosine, or tangent, we're going to look for one that has both an adjacent side and an opposite side included in it. And which one of these has that? Well, that's just our TOA here, so we're going to be using tangent. So if we erase this here, just so I have room, I can set up an equation where I say, hey, the tangent of my angle here, theta, so the tangent of theta is equal to my opposite side over my adjacent side. So my opposite side here is r sub y, and my adjacent side here is my x component. So I have my y component, my opposite, or 2.5, over my x component, 4.33. Those are meters per second and meters per second. All right, but now what do I do? Because I'm trying to solve for theta here, right? But theta is hidden inside by this tangent. So just like if I have, you know, an equation like 3x equals 1 and I want to solve for x, so I have to divide away this 3. Just as the opposite of multiplication is division, here I need to figure out what the opposite of tangent is. And because mathematicians are not always the most clever at naming things, what we call the opposite of tangent is just inverse tangent. And the way we notate that is by writing tan exponent -1 of something, and in this case, tan of theta. So we take the inverse tangent of our tangent of theta, and our tangents cancel out, and we're left just with theta. And then on the left side, we take the inverse tangent of 2.5 over 4.33. And this is something that you plug into your calculator, and whenever you do that, making sure you are in degrees, not radians. That's just a common calculator error people often make. You end up finding that theta is equal to 30 degrees. And since we started out with the same x and y components that we ended with on our last video, it's pretty dang good that we end up here with the same r and theta that we started our last video with. So now we know that our theta is 30 degrees. We know our magnitude of our vector is 5.0 meters per second. So hey, we've solved for both the magnitude and the direction of our vector, and that means that we are done. So that's all there is to it. Thank you so much for sticking with me through all that. Y'all are troopers. I hope all of your practice of all of this goes well, so happy physicsing.